Hello, everybody. My name is Pietro Abate. I'm talking here for the Mancusi project. That it's a project that recently concluded in about 6 months ago. It's a project about trying to manage the complexity of open source distributions, and in particular component-based systems. There are other people working with me in this project. One is Ralph Trinan, then Jaap Bonder, Stefano Zacchiroli, Roberto Di Cosmo, Jean Bouillon, Yassine Boussat, and other people in Paris. So why we come over here? The Mancusi project has been academically a really successful project. Has been very well rated by the European community, and everybody clap hands, and we're very happy about our job that we've done over there. It's a bit of but one main goal of this project was to reach on the developer community and to try to integrate our work in open source distributions and to try to make a difference. After all, this is a European project that's been funded with your money, and it would be nice to actually benefit about the results of this project. So the Mancusi project is finished about 6 months ago, and we developed a bunch of tools that today I'm going to present. I'm not going to go in the specificity of every tool and every small algorithm, and there is a lot of academic blah blah published on our website. Today what I'm going to present is just how you can use and how you can benefit from these tools. So what we wanted to do was to basically work on four different aspects of software distributions. One, we wanted to detect those packages that were broken, not installable. This is already part of an old project that was the predecessors of the Mancusi project, that is called the EDOS project. And probably many people here know about the utility EDOS disk check, that it's in Debian, Mandriva, and Kexamagic and other distributions. Another novel tool that we developed recently was a package to detect those packages that need manual interventions because their metadata is outdated, and there is no other ways of fixing this package than to change the metadata. So this is basically a subset of the broken packages in the first category. Then we wanted to give a step to try to detect those packages that are somehow important in the distributions, just looking at the metadata. These packages are those packages that, if changed, they're going to break or affect a large number of other packages. And just by looking at the dependency web, this is a bit difficult. So we try to actually shed a bit of light on this problem and try to untangle this web. And the last point is we wanted to actually see and guess what happens in the future if we modify, if we upgrade a package to a newer version. So this is a kind of go in a direction of predicting what is going to happen in the future when we upgrade just one component or a class of components. So the first tool that I'm going to present is this check. This check has a bit of history because it's been developed for the EDOS project back in 2005, and the first version was a standalone tool written by Jean Bouillon. Then it's been integrated in the suite DOS. It's an OCaml library that it's meant to study dependencies for software distributions, and nowadays just on component-based systems, not just focusing on software distribution. It's more general, even though here we look at software distribution in particular. In 2006, we uploaded EDOS DevCheck in many distributions and has been integrated in many QA tools so far. And then in 2009, we started rewriting those suite and as part of this this check. So the feature of this check, it's just a tool to detect which packages cannot be installed. How we do it, we encode the entire distribution in a SAT solver. We use a bit of logic, and we use a specific SAT solver that has been written for this purpose, that it's very fast and performant, and allow us to answer this question in a matter of a few seconds. Yeah, it accepts different input formats. So as I was saying, it's not just for one distribution, but we can talk with Debian, RPM, and now we can also look at the Eclipse plugin system, that it's another component-based system, and other formalism that we're going to add in the future. So it handles compressed archive, so we don't have to bother about bzip or gzip or anything else. It uses UDF. UDF, it's a generic format that try to be one of these interchange format for all the metadata in different distributions. What we do, we translate the different inputs in CDF, and then we use CDF for the analysis. This allows us to be more modular and to add backends as they come. One goal of this check was to be easily scriptable. So we choose YAML as output format, and that it's a nice format that can be interpreted by a human and easily parsed by a machine. And list, it's twice as fast as its predecessor, and there is still a bit of room for improvement. This is very good, as if you have 10 architectures and 5 releases, and I don't know what, you want to not to spend half a day testing if your packages are broken or not. So the output of this check more or less look like this. It's you have a list of packages where you have a report for every broken package, and at the end they give you the number of background give you few informations. These are the total number of packages that you analyze. These are the number of broken packages that are not installable. And these two are the foreground and the background packages, as you can specify, for example, use, I don't know, about 20,000 binary packages, but analyze only 10 of them. And in this way, it's a nice way to select which package we want to focus on. If we go deeper, I give you 2 examples of how a package can be broken. So in this case, a PTRPM repository is broken. We have different informations, and the reason why this package is broken is because there is a dependency that is not satisfied, basically, because this package is not in the archive at the moment. Another example that it's a bit more complicated. It's an example of a conflict. So he said that the GForge Web Apache package cannot be installed because there is a conflict between these 2 packages. And on the other hand, we have the chain of dependencies, because when you have a conflict between 2 packages, it might be not a conflict that is direct to the package that you're looking at, but it can be hidden deep in the dependency tree. And our tool kind of give you how to reach that package and show you that there is a conflict between this package that you're trying to analyze and the Python 2.6 minimal that is deep in the dependency tree. So as I said, it's easily scriptable, and if you want to load the output of this check, you can extract very easily all the information with a few lines of Python. And if you wonder, actually, it's useful. For example, this is the core of Ubuntu, where one package is not installable because it depends on a package that is outside the core. And while the core is meant to be self-contained, it depends on FGLRX, that it's a non-free component. So you can get somewhere you can have nice results. So a demo. So I've prepared a few comments, and I'm going to run a few of them with you just because they are nice and fast, and a few others are not going to show you the result itself. Here, what I'm going to do is to run this check. I'm going to ask it to give me all the packages that are broken, to give me explanation, to tell me something, to show me the progress, and I'm going to tell to us to analyze what's in my machine at the moment. And if I cut and paste this and I run it, it takes about 5-6 seconds to do it. At least he did it this morning. So what it does, I initialize the solver and then I start spitting out all the packages that are broken. And as you might notice, today there are a lot of broken packages. There are about 300 broken packages in Debian Unstable. If you don't ask to print everything on screen, maybe it's a bit faster. Okay. I love to demo automatic tools because they they don't require too much effort from me. So where is it used? It's used in Embedding to check in the tool chain of Embedding. It's internally used by the Mandriva QA team and the Caxamagica QA team. It's the engine of Debian Weather that you might have heard of, that it's maintained by our team. And I recently discovered that it's used in Simple CDD, that it's a small utility to create custom Debian installation CD. And in file conflicts, that it's another small tool written by us. So another something else about problem detection, it's Debian build check. Now, when using this check, we're just basically looking only on the binary packages, but this problem can be extended also on the source packages, and we want to make sure that before actually trying to build a package, we're going to be able to build a package. Otherwise, we're going to maybe set up a virtual machine and download all the packages just to find out that there was one package missing, and all this time was just wasted. So what we do is we encode the build dependencies as normal dependencies, and then we run the same tool on this encoding. These allow us to discover if a package can be installed or not. It runs a bit faster. This is an old application as well from the EDOS project. It runs a bit faster than EDOS build check. That it's just a wrapper around EDOS this check, and has the same output of this check. That is YAML, etc., etc. So an example of this tool. It's very similar to what I've shown you before. Now you've seen that certain packages have a small prefix that is source semicolon and name of the package, and basically tells you that this is a source package. And what we have done is we try to see if all the build dependencies of this source package is actually they are satisfied. And here we found that this package cannot be installed because it in their build dependencies, it depends by two packages that actually are in conflict with each other. And this is one of the small problems that we can find compiling packages. So the second demo that, as you might have guessed, is not going to be too exciting either. It's about this one. So here, oops, here I'm using all the binary packages in Debian Unstable, and trying to recompile all the source packages in Debian Unstable, looking at only one architecture, and I want to know the broken packages and have some kind of explanation from it. So now, this one it's a bit slower because before we were analyzing about 35,000 packages. Here we are jumping and we are analyzing about, I think about 50,000 packages or something. I forgot progress and stuff. Minus V, minus. So we analyze the source file, and then we analyze the binary packages, and then we encode the build dependencies. So here we analyze about 36,000 packages, and there are a lot of broken packages up and down. Outdated packages. So the first two were two applications that were already known. It's kind of easy to figure out what they are doing because we're just looking at the broken packages. Outdated packages look for a subset of the broken packages that require manual intervention. And I'm going a bit deeper here to explain what manual intervention means. So a package is broken for basically two reasons. Either it's a transient problem, so it depends on the package that is not available, or it depends on a package that is not installable. But we also have non-transient problem. These are the problems where the package itself needs to have its metadata fixed to be installable again, because maybe it depends on a package that is never going to be in the distribution again, because this package has become outdated and a new version of the package has been already uploaded in this distribution. So I have to change the metadata in order to fix this problem. So I'm going to give you a couple of examples. So for example, here we're focusing on the package foo. If you look at foo, that depends on the package bar version 2. And we ask the question, is this going to be installable in the future? Well, the answer is clearly yes. We don't have to do anything on foo. We just need to upgrade bar to version 2, and foo is going to be installable again. This often happens when we upgrade a new package that depends, for example, on a package. Well, I'm talking in Debian experimental, and we need to wait for the new package to get in Debian unstable. So there is a small delay, and we don't have to do anything on anything to foo. We just need to wait for bar to version 2 to appear. If we change a bit the situation now, bar depends on a version that is less than 2. So doesn't matter what bar is going to become in the future, for example, version 3, version 4, version 5, foo is never going to be installable because I need something that is smaller than 2. So in this case, I need to change this metadata to make sure that foo is going to be installable again. So if we go in a more complex example, so we look at foo and we have package bar and package bus. Now the dependencies are a bit more complex, and the question that we ask is always the same: is foo going to be installable in the future? Surely it's not installable now, because either depends on bus version 2.5 or bar version 2.3, and on bar and bus. But in the future, we can kind of think of a situation where the package foo is going to be installed without requiring any modification to the metadata of foo itself. Because if we go to a future where bus is of version 2.5 and without any conflict, because in the future packages can evolve in any way. So we can imagine that the package bar in version 2.5 drop the conflict. Here we are taking an over-approximation here. Packages sometimes they are a bit more conservative. And we get a version of bar of version in between 2.6 and 3, then this constraint up here is going to be satisfied. So this is another situation where even with a complex constraint, we can kind of figure out what is going to happen in the future. However, if we look at the situation like this, now the package full requires manual intervention. Because if we choose, now here we have two possibilities. Either we choose bar, or either we choose bus, or we choose bar. If we choose bus of version 2.5, this is going to select this package that is going to be in conflict with bar 2.5, and this is going to be in conflict with this constraint up here. If we choose bar 2.3, then this is not possible, because if we choose bar 2.3, I have to choose something that it's less than 2.3 here, but in the repository I have version 2.5. So these are all these kind of strange situation where we can bump into, and we developed a tool to actually identify all these packages, mainly foo, and try to flag the author of this package that this package needs its dependencies to be modified in order to be installable again. So now, cut demo. So here, oops, here again, I'm going to run this tool, and this tool is going to take a bit longer. It basically uses the same engine of this check, but this time, since I have to consider all possible futures, all possible way of how these packages are going to evolve, I need to consider a much larger universe, and in this case, it's going to be about 80,000 packages. I also try to make sure that I consider the source clusters, so I don't let packages to advance one by one, but in clusters, because we don't want to end up in the situation where, for example, I have a version of GNOME 3 and a version of GNOME 2 in my distribution. I want either GNOME 2 or the cluster of GNOME 3 altogether. This is going to take a bit of time, and okay, we're going to come back to that. So now I've been talking about these three tools that are meant to detect broken packages, to flag maintainers about broken packages, and to try to release distributions that where every package can be installed. Now we're going on something that it's more on the try to figure out how the distribution is going to evolve, and what are the important packages, and how packages can evolve, and what they will break in the future if they evolve in a certain way. So the first thing I want to do is about talking about this concept of strong dependencies. We already talked about it, I think, about 2 years ago. And this kind of came back a while ago. I was at LinuxConf Australia, and one of the release managers of Ubuntu gave a presentation that was exactly about this. So I raised my hand and say, we have all the solution of your problems. And so since this seems relevant to them, I wanted to come back to it and to try to explain what this is all about. So the idea is to try to understand which packages are important for our distributions. This is the notion of important is related if I have a bug in a package, which other packages are going to be impacted by this bug. So it's kind of try to understand how a bug spread in my distribution. Or if I upgrade one package, which other packages are going to be impacted by this upgrade. So if I look only at the web of dependencies, this is a bit too coarse, and it's a bit too complex for a human to analyze. What we wanted to have a certain measure of the packages that are going to be affected by a change. So we define the notion of strong dependencies and the notion of impact set. The impact set are those packages that are potentially affected by changes in a given package. So it's a kind of a measure of how sensitive is this package and how careful we need to be when touching this package. If, as I said, if we get the direct dependencies too little, if you get the transitive closure of all dependencies, it's too much. So we want to we need a stronger definition. The definition of strong dependency is actually very easy. We say that P is strong dependently on Q if it's not possible to install P without installing Q. So let's consider this small graph. In here we have packages that they have either a disjunctive dependency, or they have a direct dependency. Or in this case, there is a conflict between Easy and George. And here at the bottom, we have Charlie and Dog that both depend on Fox. So what we want to do is to actually try to understand which are the important dependencies, which are the strong dependencies, and which are all the others. So in this case, George, George is a conjunctive dependency. So in order to install Able, I must install George because I really need it. But if I install George that is in conflict with Easy, automatically these dependencies can never be satisfied. And this implies that Baker must be installed all the time. And at the same time, since Able depends both on Charlie or on Dog, and both of them depends on Fox, Fox must be installed all the time. So we end up in a situation where Able, in order to install Able, we always need Baker, George, and Fox. Doesn't matter what. So this gives us a way of trying to find out which are the packages that are really, really important. And then we kind of end up with a kind of a table where we can have this list of packages that where we show the impact set of for each package. When we compare the impact set to the direct dependencies, actually, we found out that the direct dependencies didn't tell us a lot of things. As we in the first five, we have packages that maybe don't have that many direct dependencies, but they have a lot of packages that depends on them. And so if we touch them that are really at the bottom of our web of dependencies, we're going to break a lot of packages because these dependencies are going to be propagated upward. And this gives us a nice notion to say, if I migrate DPKG to a newer version, probably I'm going to break about 13,000 packages, or at least this is a very important package. If I'm going to upgrade this to a newer version, maybe I need to check that all the packages that strong depend on him, they're going to be compatible with this migration, with this upgrade. Another, this is on the strong dependency side. We also have kind of a notion of, that I'm not going to present today, but the notion of domination. So if if you look at the dependency, the web dependency of a distribution, you can kind of think, what if I run one of the Google rank algorithm on this bank on these dependencies? This is going to give us the packages where most of the other packages depends, and it's going to give you this kind of hubs everywhere. What we've done is we have used a similar notion of strong dependencies. So we have run a flow graph algorithm where we were able to find out the important packages, even if those were hidden under other packages. So imagine imagine if there is a very, very important package where everybody depends, but this one depends on another one. This means that actually there is one package hidden down there that is not detected by our previous analysis. This dominator algorithm allows us also to untangle this kind of hidden packages and try to find out a bit more about the structure. The last tool that I'm going to present, it's the challenge packages. Here we're going to try to predict what is going to happen if, and since it's a prediction about the future, it's going to be an over-approximation. So I'm not going to go deep in how we did it, as I don't have enough time today. But what we wanted to do, it's we wanted to have a bit more than what we had with the strong dependencies. With the strong dependencies, we had this notion of impact set and trying to understand which packages were important. Now we want to answer to this question. What if we upgrade the package P to a version of a version V to a future version? And how many packages are going to be affected by this upgrade? And in particular, the main problem is which future version I'm going to consider, because I can't consider all the future version as it's. I mean, the future it's infinite. I have to try to find out specific versions that, in relation with my repository today, are going to be the most important tomorrow. So, as I said, I wanted to do this, but only by looking at the current repository, and I'm not going to use other kind of sources to predict how the packages are going to be upgraded. And I also want to be consistent with the clustering information. So packages don't are not upgraded by themselves in isolation, but are always upgraded in a cluster. So all packages that stem from the same source package, they're going to be upgraded all together. And this in the challenge at the moment, it's very Debian specific because of this reason, because we did this clustering analysis on the Debian packages. I'm sure that it can be done also on the RPM packages. And the idea that in Debian packages of the same source probably have the same version. This is not a rule anywhere, but if they have the same versions, they are going to evolve all together. If they don't have the same versions, then all bets are off, because we can actually predict how these packages can move all together. So what we find is that by analyzing source clusters, most of them, they move all together to a newer version. Some of them, from a source package, you have different subclusters, for example, with different epochs. Some of them, from a source package, they have binary packages with versions that evolve in completely different directions. And in this case, we really can't say how different, how these packages and versions are going to evolve in isolation. So This challenging algorithm, it takes some time. It's not something that you want to do on your machine. It's something that distributions want to run once a day. It takes about 35 minutes, 40 minutes, a bit too much for a demo here, but I kind of give you the idea of how packages are going to evolve. And this is particularly useful if you have point-wise distribution and you want to modify only specific packages. Then once in a while you want to run this algorithm and kind of to see I'm here in this point in time with these packages, and I want to migrate this component of my distributions. What is going to happen when I do that? So, as I said, we have source packages with versions, and then we have target versions. The target version is this idea, what is going to happen when I upgrade to a version that is bigger than. So, in this case, the first four, so these are for Debian Squeeze. And we see that in Debian Squeeze, one of the most problematic one package that emerged as problematic dependency-wise when upgraded. It means that the dependencies on the Perl package are very tight. Is this one, but is this one for many different reasons. So if we upgrade from this version to a version that is in between 10.5.2 and 10.12, I break 652 packages. If I upgrade to a version that is in between here, I break as many. But if I upgrade to a versions that is in between this one, then I break a bit less. This basically is telling me that the upgrade to a specific version is going to break a number of packages, but not all the upgrades are the same. So Python is also another one. I mean, there are many different examples. If you get glibc, if you migrate to something that it's larger than 2.12, I'm going to break about 400 packages. If I migrate something that is in between this version and 2.12, I'm going to break a bit less packages, and so on and so forth. This tool gives us a way of kind of peeking into the future and trying to understand what is going to happen if we migrate to a specific version. So when actually going to change a component of your distribution and you run this algorithm, you might be careful at where you're going to end up with your migration. So one last tool that I'm going to present. Actually, I'm not going really to present, as it's a bit outside the scope of this presentation. It's the coinst tool that has been developed recently by one member of our group, and it's a tool to compute the installability kernel of distribution. What are the installability kernels? So if we want to understand about how packages can be co-installable together. In particular, we find out that in Debian, about 80% of the packages can be installed together. If you want to find the largest installation with the Debian packages, you probably can install in Debian Unstable about 30,000 packages altogether. But there are a number of packages that they can't coexist together. And what this tool does is try to identify this class of packages that can coexist together. So, for example, think about the mail agents. You can't install sendmail and postfix at the same time because the conflicts, the structure of conflicts doesn't allow you to do that. This is a simple example about two packages or actually it's a family of packages that cannot coexist together. But if you look carefully at the distribution, there are not that many family of these packages that cannot coexist together. And this tool just allow you to identify this class of packages and to have a simple graph to analyze what's how the structure of conflict actually works in your distribution. These are all kind of hidden structures that we are trying to let surface, to allow people to look a bit at the general picture. So it's been written by Jean Bouillon, and if you're interested, there is a website with a lot of explanations and very nice graphs. So my presentation finished here, that I think it's about 45 minutes, and I'll be very happy to take questions.
Classification of important modules or packages, how many levels do you go? Do you take the whole installation level, or do you just
Yeah, it's the question was about how deep we go in the dependency graph. We consider the entire dependency graph. We consider the entire distribution. Give me one package file that it's our universe, and we consider all the packages. And with our tool, I think we analyze universe that are up to 100,000 packages. So I think we are in a good position to scale.
What
Can you wait for the mic?
timescale does that take?
The question was about how long does it take? For 30,000 packages, it's about 5 seconds. 80,000 packages, it's about 2 minutes.
Thank you very much.
Yes.
Do any of the tools that you developed have the capability of working with packages different than Debian's?
Yeah, we work with, this check accept Debian, HDList, synthesis file, CUDF, that is this interchange format, and Eclipse file. And once upon a time, I had also a filter for BSD, but has not been rewritten at the moment. All these tools are, so every year we promise a release. This year, actually, we are very, very close. We are so close that there is a release of the source code on our website. And we are so close that there are packages in Debian Experimental. And we are so close that Ralph is working right now to to finish up the Debian package that it should be up sometimes next week. So this is a way to put a bit of pressure on ourselves, because we say we're going to release these tools and then we never do it. Okay, thank you very much.